Download this code from codegive.com, link in the description below. OK, let's dive deep into the concept of refine and how it might evolve in the future, especially in the context of code. We'll cover the fundamental idea of refinement types, how they're currently used, the potential for more advanced applications, and provide code examples to illustrate key concepts. What is refinement? At its core, refinement in the context of programming and data science refers to the process of making something more precise, accurate, or specific. It's about taking a general concept or structure and adding constraints or limitations to make it better suited for a particular purpose. Think of it as taking a raw, unpolished gem and carefully cutting and polishing it to reveal its brilliance. In programming, refinement often involves tightening the types of variables, function parameters, and data structures. It goes beyond the basic type systems of many languages, example int, string, bool, to provide more precise guarantees about the values that these types can hold. Refinement types, the foundation. Refinement types are a specific kind of type system extension that allow you to express constraints on the values a type can take. They build on existing type systems. Example, conceptual. In a language with refinement type support, you might be able to write something like this, using a hypothetical syntax. In this example, positive integer is a refinement type. It's an int, but with the added constraint that the value must be greater than 0. The divide function now has a stricter guarantee, its denominator will never be 0, which can help prevent runtime errors. Benefits of refinement types asterisk. Asterisk early error detection asterisk the compiler, or type checker, can catch errors at compile time that would normally be runtime exceptions, example division by 0, out of bounds array access. Asterisk improved code reliability asterisk by encoding more precise constraints into the types, you make your code more robust and less prone to unexpected behavior. Asterisk enhanced code documentation asterisk refinement types can serve as executable documentation, clearly stating the expected preconditions and postconditions of functions. Asterisk optimization opportunities asterisk compilers can potentially use refinement type information to perform optimizations that would not be possible with only basic type information. Asterisk formal verification asterisk refinement types can be used as the basis for formal verification systems, allowing you to mathematically prove the correctness of your code. Current implementations and libraries. While refinement types are still not a core feature of many mainstream programming languages, there are several ways to incorporate them into your projects. 1. Dependent type languages languages such as Idris, Agda, and F are built around the concept of dependent types, which are closely related to refinement types. These languages provide very powerful type systems that can express complex constraints. However, they often have a steeper learning curve and are not as widely used as languages like Python or Java. 2. Libraries and tools there are libraries and tools that provide refinement type-like functionality for existing languages. Here are some examples. Python MyPy and type hints while MyPy itself doesn't directly support refinement types in the fully fledged sense, you can use type hints and assertions to achieve some similar effects. You can also use libraries such as BearType to implement runtime type checks using decorators. Z3, SMT solver you can integrate Z3, a powerful SMT, satisfiability modulo theories, solver, into your Python code to perform more sophisticated type checking and constraint solving. This is a more advanced approach, requiring knowledge of logic and formal verification. Java Checker framework. The checker framework is a Java compiler plugin that allows you to add custom type systems to Java. It includes support for nullness checking, immutability checking, and other forms of static analysis. It can also be extended to support refinement types. Scala refined. The refined library allows you to define refinement types in Scala using predicates. JavaScript/TypeScript IOTS. This library lets you define runtime validators for your types. While not static refinement, it adds runtime validation and can catch errors that TypeScript misses. Code examples. Let's illustrate some of these concepts with code examples. Python, using type hints and assertions. In this example, positive integer is a new type that's logically an integer. The create_positive_integer function enforces the constraint that the value must be positive, raising a value error if the constraint is violated. While Python's type system won't automatically enforce this at compile time, using MyPy, the runtime check provides some protection against invalid values. Scala, using the refined library. In this Scala example, the refined library allows us to define positive integer as an int that satisfies the positive predicate. If you try to create a positive integer with a negative value, the refineV function will return an error. TypeScript, using IOTS for runtime validation. Here, IOTS is used to define a positive integer type that is validated at runtime. The decode method attempts to validate a value against the type. If validation fails, an error is reported. The future of refinement, more powerful and integrated systems. The future of refinement in programming involves several exciting trends. 1. Deeper integration into languages. We're likely to see more languages incorporate refinement types as a core feature, rather than relying on libraries or extensions. This will make refinement types more accessible and easier to use. 2. More expressive type systems. Future refinement type systems will be able to express more complex constraints. This could include temporal constraints. Constraints on the order in which functions are called or the state of a program over time. Data dependencies. Constraints that relate the values of different variables or data structures. External data validation. Integration with external data sources for dynamic validation of input. 3. Automated constraint inference. Instead of requiring programmers to manually specify all refinement types, compilers will be able to infer them automatically. This will reduce the burden on developers and make refinement types easier to adopt. 4. Better SMT solver integration. SMT solvers, like Z3, will play an increasingly important role in refinement type systems. These solvers can automatically prove that code satisfies complex constraints, making formal verification more practical. 5. AI-assisted refinement. AI could potentially assist in automatically refining code, identifying potential errors, and suggesting appropriate refinement types to improve code quality. 6. Security applications. Refinement types can be used to enforce security policies and prevent vulnerabilities like buffer overflows and SQL injection attacks. This is an area of growing interest. Example of a possible future, hypothetical language. Let's imagine a language called Clarity that has built-in refinement type support and advanced features. In this hypothetical example, the language has a built-in way to define refinement types using the where keyword. The compiler can automatically validate that values conform to the constraints specified in the refinement types. The try-convert function handles the case where user input might not be valid, using a maybe type, similar to optional in Java or option in Scala, to indicate success or failure. Asterisk the match statement allows you to handle different cases based on whether the email and subject are valid. Challenges and considerations asterisk. Asterisk performance overhead asterisk runtime checks for refinement types can introduce performance overhead. Careful optimization is needed to minimize this impact. Static verification, compile time, is always preferable. Asterisk complexity asterisk refinement type systems can be complex to understand and use, especially when dealing with intricate constraints. Asterisk scalability asterisk as the number of refinement types and constraints increases, the verification process can become computationally expensive. Asterisk integration with existing code asterisk integrating refinement types into existing code bases can be challenging, especially if the code is not well structured or uses dynamic typing. Asterisk the halting problem asterisk some constraints might be undecidable, i.e., there is no algorithm that can determine whether they are satisfied. This can lead to the compiler getting stuck in an infinite loop. Conclusion asterisk. Refinement types represent a powerful and promising approach to improving the reliability, security, and maintainability of software. While they are not yet mainstream, they are gaining traction and are likely to play an increasingly important role in the future of programming. By incorporating more precise constraints into the type system, refinement types enable earlier error detection, improved code documentation, and potential optimization opportunities. Keep an eye on developments in this area as languages evolve and new tools and techniques emerge. Experiment with libraries and tools that offer refinement-like features to gain hands-on experience and prepare for a future where code correctness is more rigorously enforced by design.